Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math basic course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside as we explore the Chapter 5 review in the Big Ideas Math Integrated Math 2 textbook, everything relating probability. Only 18 problems as a whole, but they do some example problems leading into each section, sections 5.1 to 5.6. They'll be laid out in full, and I'll go over those examples as well as the problem set. No lecture notes beforehand outside of the examples, and let's see how much they teach us. Otherwise, you should be well prepped in what you're doing, just working on the review. Follow my solution guide, download the PDF below if you need to do that, and take a look at the timestamps to find each timestamp for, I think I just said that, for each question that we're doing. Without further ado, guys, make sure you have your calculator. We're going to go ahead and get started. We're going to look at section 5.1 on sample spaces and probability. And here's the example that they're giving. Each section of the spinner shown has the same area. So blue, red, yellow, green, orange. 5 things. The spinner was spun 30 times. The table shows the results. So this is an example of something called experimental probability, whereas theoretically we could figure out what kind of chances we have of landing on something. For which color is the experimental probability of stopping on the same color as the on the color the same as the theoretical probability? So each color has the same area, so there are 5 different colors. They all occupy 1/5 of the entire thing. So which of these, if spun 30 times, lands on the same 1/5 fraction is basically what we're looking at. This is theoretically, they each have a 1/5 chance. Experimentally, green has a 4/30ths chance, which is 2/15ths, not 1/5. Orange has 6/30ths, which is 1/5 when reduced. So it looks like orange would be the answer, should be the answer there. Red is 9/30ths and reduces, and this is a good way of showing that you should be reducing your fractions. 8/30ths for blue, 4/15ths, 3/30ths for yellow, 1/10. So orange is the one that's the same as they asked, and yeah, that one seems to fall in line and match up. So we go to our questions now. We look at question number 1, and you record a person's gender and whether they responded yes, no, or maybe to a survey question. How many possible outcomes are in the sample space? List the outcomes. So this doesn't have to do with theoretical or experimental probability. What tends to happen in these section things is they give an example of something. They try and cover the umbrella of it, I guess. Not always. And then you get some different questions. Sometimes they don't have to do with the example, but at least you got more coverage. All right, what they say, you record a person's gender. I'm going to assume they're talking about either male or female. So we're going to choose between male and female, and they say yes, no, or maybe when it comes to responses. So when a person does a survey, they can either say they're male and say yes, male and say no, or male and say maybe, or female and say yes, female no, or female maybe. In that case, there are six total possible options in that sample space. And it really is just 2 times 3, right? 2 times 3. That's something that you kind of learn over time as you do those arrangements. All right, number 2. A bag contains 9 tiles, 1 for each letter in the word happiness. Yep, happiness is 9 letters. Confirmed. You choose a tile at random. What is the probability that you choose a tile with the letter S? Well, probability of S, out of 9 tiles, 2 of them are S's, so you get a 2/9 probability for that one. Is that part A? Sort of. There is a second part they just don't have them labeled. What's the probability you choose a tile with a letter other than P? So, well, other than P. So P naught is going to be 1 minus the probability of P. So 1 represents the 100%, and then we take out the 2 P's that are there from the 9 tiles, and that gives us 7 other letters other than P out of the 9, and that's the probability we choose a letter other than P. Number 3. Using the spinner above, what are the odds in favor of stopping on yellow? What are the odds against stopping on blue? Well, do we use they said the spinner, not the table, so I'm guessing we're talking about the theoretical probability in this case, each which has a 1/5 chance, but they're mentioning odds. So on number 3, odds in favor of yellow. Sorry, I'm going shorthand. Odds in favor of yellow. You have a 1/5 chance of stopping on yellow and a 4/5 chance of stopping on anything else. That makes it 1 to 4 odds in that case. 1 for yellow, 4 for everything else. So odds are not favorable out of total. They're favorable out of unfavorable, represented as a ratio instead of a fraction, which ratios are fractions. Now they say odds in favor of blue against blue. Odds against blue It's going to be the same thing, only you reverse the result. So you have the unfavorable first and favorable second. This should be 4-1, given that there are 4 other colors other than blue, and then blue's the other color there. Just working on the odds portion and favor versus against. That should be number 3. And that's part of the sample space stuff, or at least the first one, was a part of section 5.1 for probability. All right, section 5.2, before we do the 4, 5, and 6, let's take a look at the examples they give on independent and dependent events. Okay, you randomly select 2 cards from a standard deck of 52 playing cards. What is the probability that both cards are jacks when you replace the first card before selecting and you do not replace the first card? Compare the probabilities. So they do these examples here. You have something that's known as an independent case for the first one, because having the second probability is not dependent on the outcome of the first thing. When you replace the card, bring it back in the deck, all bets are off and you're back to where you were. So the probability of selecting a jack again is equal as it was before. Now, there are 4 jacks in the deck out of 52. And then the AND case is you multiply these 2 things as well. So 4 out of 52, which is 1/13th, times another 4 out of 52, or 1/13th. They went full bore, and this is the 1/13 times 1/13th, and 0.006, that's around 0.6%. Rather low odds for getting 2 jacks in a row. Now, the odds should be even lower, actually, lower? Yeah, lower if you draw a jack, do not replace it, and then draw another jack, because what you had before was 4 out of 52. But then you only have 3 jacks left out of 51 cards, and 3 out of 51 is lesser of a percentage than 4 out of 52, because you lost a jack, and you're trying to see getting another jack after that as well. So 4 out of 52 times 3 out of 51 is reduced to 1 out of 221. It's about 0.5%. Not much lower, but a little bit lower. And lower matters in that case. So independent versus dependent events, the second one's dependent because the probability of jacks now depended on whether or not you drew a jack, or what you drew the first time in general, because now there are less cards and in that case less jacks. All right, let's take a look at the 5.2 stuff. Let's now jump to number 4 as we do this. See, this looks like the thing we did before here. Find the probability of randomly selecting the given marbles from a bag of 5 red, 8 green, and 3 blue marbles when you replace the marble before drawing the second and do not replace, and compare the probabilities. Oh, by the way, I didn't mention this for the example thing. They do say how many times more this is than that. 0.6% versus 0.5% is not just 0.1% more. It's a certain number of times more as well. You can divide 0.6% by 0.5%, or the fractions. You're 1.3 times more likely to select 2 jacks if you do replace the card. So we're going to have to do the comparison as well. They do say compare the probabilities. All right, so before we start numbers 4, 5, and 6, let's first just get the total amount of marbles here. Total is going to be 5 red, 8 green, and 3 blue. That's 16 marbles. So everything we do divides out of 16, whereas the playing cards, there are 52 to begin with, something we should kind of universally know. All right, so red, then green, and that's specifically first red, then green. So when it comes to replacing in the independent case, the probability of red, then green is going to be 5 red out of 16, and then you replace it, times 8 green out of 16. That's 5 out of 16 times 1/2, and which is 5 out of 32. Now that is the fraction version. It seems like they're going to the calculator for these, so I'm going to go ahead and do the same thing. So 5 out of 32. I'm getting 0.15625. I'm more inclined to do the percentage, 15.625%. Now that's exact. There was no rounding on that one, so let me actually put exact on that guy there. Now, what if we do not replace? We do not replace, meaning you don't put the marble back after. Probability of red, then green, means we take out a red marble. We had a 5/16 chance of doing that, and we leave it out. Now there are only 15 marbles left, but there are still 8 green marbles remaining. So instead of 8 out of 16, it's 8 out of 15. Now this 8 out of 16 I can reduce to 1/2, and 5 out of 15 I can reduce to 1/3. 1/2 times 1/3 gives me 1/6. And 1/6 is about, as far as the percentage goes, 16.67%. Just kind of something you got to know. Now compare them, right? Let's compare. 5 out of 32 is what's the smaller of the numbers? Let's see. I don't know which way we're supposed to. Do we always have to do the bigger one? The one that's bigger? The 1/6 is bigger. So 1/6 divided by 5 over 32, which is 1/6 times 32 over 5. You multiply by the reciprocal, which reduces to 16 over 3. 16 over 15. I don't know 16 over 15. Rounds to 1.06 repeating. So I'll say 1.07 times more likely. Hold on. Let me do this down here. I'll type it. You are 1.07 times more likely to draw red then green if you do not replace the red marble first. So if you do not replace it, you're more likely to do it than not. About 7%. Wait, do they say is percent? No, they say times. Not much, but more likely. All right, number 5, blue then red. Now that we see the idea, we can go pretty fast with it in general. So number 5, blue then red. I'm going to write it out first that way, and I'll say probability of doing it where you replace. I know I'm kind of doing it backwards. Probability of replacing blue then red. So you have 3/16 chance of doing blue. When you replace it, you got a 5/16 chance of red. That's 15 over 16. I should know that value. It's somewhere 9, I don't have it, 9375 or something. Let's see. 15 out of 16. 0.9375, yeah. So 93.75%. So either that or that. Do not replace. Don't replace. You know, don't follow how I write some things out in this situation. This is just conversationally with me and you, how this works. I draw the blue 3/16 chance, and then I still have 5 red within there, but I did not replace the blue, so only 15 left in that situation. Now, 5 out of 15 reduces to 1/3, and 3 out of 3 reduces to 1. So you get 1 out of 6. Something seems wrong with that. Oh, this isn't 15 out of 16. Oh my goodness, I hope I didn't make that mistake in other problems. That's not, I was going to say, that's really high. I just ignored it. That's 15 out of 256. Yeah, that's significantly different. Hey, here I am. So 15 out of 256. Let's do that again. So the other one was actually fine, but that's 5.86%. About, not exact. This one on the other hand, was that 1 out of 16. So 3 out of 16 times 5 out of 15, which reduces to, again, 1/3 in this case. So that's 1 over 16, which is a little more, not much, 0.0625, so 6.25%. So once again, not replacing, you're getting a higher probability. And honestly, the only reason it's higher probability is because you're not choosing the same color twice. If you don't replace it, then the other colors still have the same amounts as there were, but there are less marbles. If you don't replace something with the same color, you lost one of those marbles as well. So now we're going to do 15 out of 256 divided by, no, let's do it the other way. 1 out of 16 divided by 15 out of 256, which is 1 out of 16 times 256 over 15. And that's 16 over 15. So 16 over 15 is 1.06 repeating. Wait, did we already see that number? That was this other number before, right? 16 over 15. 1.07 times more likely. If not replace. Sorry, you can tell that I'm kind of on a time crunch myself when it comes to answering those questions afterward, but you can calculate the same thing. Don't make the same mistake I did and say 16 times 16 is 16. All right, anyway. Number 6. Probability of green then green. So green then green. This is an example where the replacing should have a higher probability. So green then green. So probability, if you replace Green is 8 out of 16, and we're going to replace it. So we'll still have another 8 out of 16. That's 1/2 times 1/2, which is 1/4, which is 25%. We should all be pretty familiar with that one. Now this time we will not replace. Probability of don't replace. If we first draw a green 8 out of 16, then we have to draw another green after not replacing this one. That means there are only 7 greens left out of 15 marbles total. So 8 out of 16 is still 1/2. 1/2 times 7/15, and that'll give you 7 over 30. Now 7 over 30, not a great score on a quiz. About 23.3%, which is lower than the other guy. 3 repeating, of course. So let's do 1/4 divided by 7 out of 30, which is 1/4 times 30 over 7. 30 reduces to 15 over 2, and that becomes 15 over 14. 15 over 14, it's a little more than 1.07. Well, it's still 1.07 about. It's 1.07, 1/4, etc. 1.07 times, more likely, if you replace it. Meaning to get that probability. Okay. All right, those problems went a little slower as the first ones were a little faster, so let's keep moving forward and see how we do moving forward. Section 5.3 on two-way tables and probability. Here's the example. A survey asks residents of the east and west side of a city whether they support the construction of a bridge. The results given as joint relative frequencies are shown in the two-way table. So basically versions of probabilities, everything that adds up to 100% of all the survey responses. What is the probability a randomly selected resident from the east side will support the project? So we're not just looking at this 0.47. They said randomly selected resident from the east side. We're only looking at east side folk. So they make up 55% of everybody. Now 55% is the total that we want to look at. And those who support it are the east side and yes folk right here. So we're going to divide 0.47 divided by 0.55, which is about 85.5%. This is a situation where we have what's called a conditional probability. Given that we're only looking at the east side folk and not west side, what is that answer? So we'll see if they ask more questions based off that, or they have their own set to do. But that's a good example of something you can look at in general. Number 7, what's the probability? Okay, good. It's still a part of this. What's the probability a randomly selected resident who does not support the project in the example is from the west side? So now we're looking at people who do not support only. Now, 8% do not support from east, 9% do not support from west. So we're looking at a whole 17% whole. We're looking at only that 17% amount, and within there, which ones are from the west side. So probability you're on the west side, given you don't support, given that you're a no. So 9% of all are from the west side, but only 17% are those who do not support. 9% of no's are from the west side, but only 17% of all of them are no's, and this is what we're going to divide. Basically 9/17. 9/17 is 0.529 when rounded, which is about 52.9%. 52.9% are of no's are from west side. Right? The other, 47.1% are from the east side, just of the no's. And that's another conditional probability thing. Number 8, after a conference, 220 men and 270 women respond to a survey. Of those, 200 men and 230 women say the conference was impactful. Organize these results in a two-way table first, then find and interpret the marginal frequencies. So let's see. Before I would make tables, let's see. Men, women, total. I'm going to do this. I'm going to make a table thingy. I did this at the time in the section. I don't know if I have the time or luxury to do the whole, clean this up a lot. So let me just work a little bit of magic as I can. Let's get rid of that here. I'm not going to use this column. We're going to separate by gender and by, what was the other part? Conference, impactful conference. So this is between men and women. Now we're going to have these things called marginal frequencies, which represent the totals. We kind of talked about totals a second ago. And we're going to talk about impactful conference versus not impactful. Now, they said there were 220 men in total and 270 women in total. That makes 490 total people. Of those, 200 men said it was impactful. 230 women said it was impactful. That means if 200 men said it was impactful, then 20 said it was not. If 230 women said it was impactful, 40 say it's not. You can also gather these totals to 430 total that said it was impactful, 60 said that it was not impactful, and once again, 430 plus 60 is 490. That's the two-way table. Finding and interpreting the marginal frequencies. Once again, we already know that the totals from men and women are there, so I'm just going to interpret the new ones that we just found. 430 people found the conference impactful, while 60 of them did not. I'm not saying the 220 and 270 because we already said those. That's the first thing they said in the problem. So I hope that's okay. All right, that was some on section 5.3. Let's move on to 5.4. Probability of disjoint and overlapping events. Let A and B be events such that probability of A is 2/3, B is 1/3, and A and B is 1/3. 1/2 for B. And A and B is 1/3. Find probability of A or B. Now they're giving you a formula. Oh, we're not doing that problem. They're giving you the formula A plus B minus A and B. See, there's an overlap of that which represents 1/3. I don't know the scenario or context, but there are some that are from A, some that are from B that overlap each other, and we got to take out that overlap because we're counting it twice when we add probabilities of A and B. Because you can tell that 2/3 plus 1/2 is more than 1, and that shouldn't be possible. Taking out the 1/3 does that. They found a common denominator to get 5/6, which is around 83.3%. Let's do the same thing for number 9, as that example is straight up from there. They say use a calculator for the last division. We don't always have to. A and B be events such that probability of A is 0.32. Probability of B is 0.48. Probability of A and B is 0.12. So these events are not said to be mutually exclusive when this happens, because there's a chance that when A happens, B can also happen. So probability of A or B is going to be probability of A plus probability of B minus probability of A and B. So this is 0.8 minus 0.12, which is 0.68, which is also 68%. There you go. There's number 9. Number 10, out of 100 employees at a company, 92 employees either work part-time or work 5 days each week. So it's an either or on that. There are 14 employees who work part-time and 80 employees who work 5 days each week. What's the probability a randomly selected employee works both part-time and 5 days each week? So we're going to use the same formula as before, but this time we actually have the or. So probability of A or B, A being part-time, B being 5 days each week, is 92 out of 100. You know what? They say the 100 employees, should we just stick to decimals? So 0.92. So probability of those who those who do work part-time is 14 out of 100, 0.14. Probability of B, 5 days a week, they're 80 out of 100, so 80%, 0.8. And probability of A and B is the unknown. Now, as far as the formula goes, 0.92 is the A or B portion. That's on this side, and that equals adding up 0.14 with 0.8, and then subtracting that probability of A and B, of which we don't know, the overlap of those who do both. Of those who do both, we take that part out. So 0.92 is 0.94 minus probability of A and B. Maybe you're figuring it out there. We add probability of A and B to both sides. You subtract 0.92 from both sides, and we get 0.02, which is 2%. 2 out of the 100 work both part-time and 5 days each week. Okay, section 5.5. We keep moving forward. We only have, we still have 8 questions left, but maybe these go a little faster. We'll see. Permutations and combinations. A 5-digit code consists of 5 different integers from 0 to 9. How many different codes are possible? Given the fact that, whenever you type a code, like 1, 2, 3, 4, 5, and 5, 4, 3, 2, 1, those would be different codes. It's not like type them in any order. So order matters. This is where we use something called a permutation. That's what they say here. Find the number of permutations of 5 integers chosen from 10. So how many different combinations are possible? 10 pick 5. There's a formula, which is n factorial over n minus r factorial, and we work some things out. They do their magic. I'll make sure to do the same kind of thing. You can either use it in the calculator or keep moving forward. Factorial means multiply descending integers from your number all the way down to 1. But if 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1 is 1, they might as well cancel it once they hit the 5 factorial. They're left with 30,240 possible codes. That would take a while to try and break. All right, so number 11 through 14, let's evaluate these expressions. Now, permutation of 7 pick 6. I just mentioned before, it's n factorial over n minus r factorial, which is 7 factorial over 1 factorial. Now, 1 factorial is just 1, so that doesn't do anything. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. I do seem to remember it was 5040. We did this at the time. 720 times 7 is what I got to do, so I'm just trying to use the calculator in my head and do that one, and I think that's going to be it. Number 12, 13 pick 10. I'm afraid this is one that I might have to go to the calculator for. We'll see. But 13 pick 10 is going to be 13 factorial over 13 minus 10 factorial. That means 3 factorial. So that's 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, but 3 factorial works there until the bottom 3 factorial. I will absolutely use a calculator here. And in my calculator, I have a couple options in what I could do. I could literally do all those 13 et ceteras. I could also do 13 factorial over 3 factorial. And I could also confirm that this answer, which is huge, is going to be the same thing as if I did 13 pick 10. 13 pick 10 for permutations should be that same number. So let me write that out. That is 1037836,800. That is 1 billion. 1 billion. Hopefully it's not this many combinations of things. 1,037,836,800. Whew. Try that without a calculator. I shall not. Number 13. 13 and 14 are combinations, not permutations. Combinations where order does not matter, and its formula is only slightly different because there is one added bit in the denominator. We do 6 factorial over 2 factorial is added into here, and we still do the 6 minus 2 factorial portion here. So 6 factorial over 2 factorial times 4 factorial. Now, as far as working that out, this is 6 times 5 times, I'll just put 4 factorial, and 2 factorial is 2 times 1, and I'll keep this 4 factorial here, which will make them go away. We get 30 over 2, which is 15, and there you have it. And number 14, we have 8 choose 4. 8 choose 4. Remember, 8 minus 4 is also 4. So we'll get 8 factorial over this original 4 factorial and then times 8 minus 4 factorial. So 4 factorial there. So that's 8 times 7 times 6 times 5 times 4 factorial over. And I'll leave that 4 factorial there while I do 4 times 3 times 2 times 1. The reason I leave that one there is because these are going to go away. And let's keep working this out. Now let's shrink it in a reasonable way. 8 divided by 4 gives me 2 over 1. 6 divided by 3 gives me 2 over 1. And 2 divided by 2 gives me 1 over 1. So I'm left with 2 times 7 times 5 all over 1. So 2 times 7 times 5 is 70. Number 14 is 70. Okay, number 15. In how many ways can you arrange all the letters in the word uncle and 3 of the letters in the word uncle? This is where order clearly matters when they talk about arranging the letters in the word. So for part A, all of the letters, that's 5 pick 5, which is the same as 5 factorial, and that number is 120. 120 different ways for arranging all of them. But if you want to arrange just 3 of them, not a P, let me actually even throw the word uncle out here. Whoopsie. That's okay. This 5 pick 3, there are 3 spaces for which we use UNC, UNL, UNE, UC, N. It's everything, right? So that's 5 pick 3. Not everything. 5 factorial over 5 minus 3 factorial. Boom. Which is 5 times 4 times 3. The 2 factorials divide out, and you get 60. 60 different ways to arrange those guys. Number 16, a random drawing will determine which 3 people in a group of 9 will win concert tickets. What is the probability you and your 2 friends will win the tickets? So it doesn't matter which order we're winning the tickets. It doesn't matter if I'm first, my next friend is second and third, or they're first and I'm second. So this is a combination kind of scenario, but it is a probability question. They said a random drawing will determine which 3 people in a group of 9 will win concert tickets. Now, out of the total, there are 9 choose 3 of them, and it is a combination given that the order does not matter. Now, I want me and my friends to win the tickets. There's only one which way that me and my friends can win the tickets. And that's in a 3 choose 3 scenario. Of the 3 tickets, we're the 3. So let me actually write that. 3 choose 3. Of the 3 tickets, we're the 3. 3 choose 3 is 1. Now, 9 choose 3. I'm going to use my calculator for that. 9 choose 3 is 84. So we get a 1 out of 84 chance. Normally these numbers get a little small, like 1 out of 84, that the percentage version isn't worth it. It's a little more than 1%, but kind of low odds. Kind of low odds for 1 out of 84. Okay, let's go to number 7. Oh, let's go to section 5.6. 2 more questions, but let's look at what they got for us. According to a survey, about 21% of adults in the U.S. visited an art museum last year. You asked 4 randomly chosen adults whether they visited an art museum last year. Draw a histogram of the binomial distribution for your survey. So there's a formula that they use, and they kind of have it spelled out right here in each of the bits. It depends on whether we're using K as 0, 1, 2, 3, or 4. You can see the parts that change. 0, 1, 2, 3, 4 are here. 0, 1, 2, 3, 4 are here. And here you can see it's 4, 3, 2, 1, 0. Now, what are the other numbers? 0.21 is the probability of success, the 21% of adults that visit. 0.79 is 1 minus 0.21. That's everyone who didn't, 79% that didn't attend. So it kind of works out in that way. I'll let the formula be what it is. But what they're doing here is they're finding if you randomly survey 4 people, what's the probability that exactly 0 of them, that none of them say that they visited a museum? 39%. There's a 41-ish% chance that one of them will say they visited a museum, 16.5% chance that 2 of them say it, 2.9% chance to say that 3 of them say it, and 0.2% chance that all 4 of them say it. Very low when there's only a 21% chance that you get it. And getting all 4, very unlikely. Very unlikely. So they do a histogram as well. And a breakdown of the histogram just shows the percentages, probabilities as like decimal equivalents of them, and the K number of adults who visited the museum. And the histogram is the frequency of them based on probabilities. 4 is so low, so small, less than 1% that you just can't really see it. So number 17, find the probability of flipping a coin 12 times and getting exactly 4 heads. In this case, our N, the number of trials, is 12. Your probability of success is 0.5. That also means your probability of failure is 0.5. It's either heads or tails. And our K value in this case is going to be 4. We're going to find the probability of exactly 4 heads, where we're going to do N choose K times probability of success raised to the 4th power times probability of failure raised to the 12 minus 4 power. 4 heads landed on and 8 tails landed on. So we're going to calculate it that way. It's our computation. So I'm going to do in my calculator, I can do 12 choose 4 times 0.5 to the 4th power times 0.5 to the 8th power, which really is just a way of saying 0.5 to the 12th power. So I'm getting around 12.1%, 12.1%, which is kind of high as an overall when you consider the fact that you have to spread this, you have to distribute it out, not evenly, but from 0 to 12 heads that can be landed on, that the point, I think it's pretty decent stuff, pretty decent results that you're getting there as far as that goes. But yeah, so there you have it. All right, let's go to, was that just part A? What else was there? Hold on. I lost it. Nope, that was it. Number 18. Last question. A basketball player makes a free throw. You know what? I brought this up on the other thing saying I bet you they'd have basketball questions. Here is one. A basketball player makes a free throw 82.6% of the time. The player attempts 5 free throws. Draw a histogram of the binomial distribution of the number of successful free throws. What is the most likely outcome? So 5 free throws. Probability of success is 0.826. Probability of failure is 1 minus 0.826, which is 0.174, I think. I hope. And we're going to just do we're basically going to do a breakdown of all of these. Probability if K is this, and here's the template I'm going to use. I should have always done this each time. But probability of K is this. Hold on, I'm going to do this again. Probability of K equals this is 5 choose something times 0.826 to that something times 0.174 to that something. I bring up this whole thing as a template so I can clone this over and over. I'm basically going to use this exact same template and fill in different numbers for where K will exist. So I need to do it for 0, 1, 2, 3, 4, and 5. So check this out. When K is 0, 1, 2, 3, 4, and 5. This is 5 choose 0, 1, 2, 3, 4, and 5 to the 0th power, 1st, 2nd, 3rd, 4th, and 5th. And then this goes down 5, 4, 3, 2, 1, 0. Look how much faster that was. All right. Now my calculator, I can go even faster, and I intend to. So I'm going to, on the calculator, do a formula where I do 5 choose and whatever x value thing we're going to be doing, 5 choose x times 0.826 to that x power times 0.174 to the 5 minus x power. When x is, 0, then that is 5, etc. So I can do this table bit. I'm going to start from 0 and increase by 1 each time. So I can look at 0, 1, 2, 3, 4, and 5. And I see them right there. You can ignore 6 where it shows the 0. But this first probability is very, very small. This one, it's in scientific notation. I have to move the decimal 4 places over. That'll be 0.00016. That's as much as I can fit. So I'm writing it like that, 0.00016. Now let's keep moving forward and write some of these other ones down. Of 1, that's 0.00379. 2 free throws, 0.03594. Remember, these are decimal equivalents of percentages. That means that's around 3.6%, which is still low. This person's an 82% free throw shooter. It's very uncommon. They're only going to make 2 of the 5 free throws. Then 0.17062. And you might look at some of these and say, well, none of them are that high. You have to remember, you have to spread out this distribution among everything. So it's just one of those things that it needs to show in some capacity. 3, 8, 4, 5. It's not possible to do 6 when you only have 5 free throws. So 0% after that. So here are the different, here's the breakdown. I'm going to draw a histogram based on this. Now, the most likely outcome is 4 free throws, which makes sense because 4 out of 5 is closest to 80%, as is his free throw breakdown. But all of these basically add to 100%. He's a 40% chance of getting exactly 4 of them, a 38% chance of getting exactly 5 of them. You can see where that trend goes. So let's do that histogram, and then we'll be out of here, guys. Almost done. So in this histogram, we're going to go up to 40%. Let's go up to 50. 10, 20. How can I fit this best? 5, 10, 15, 20, 25. I think I can spread this out a little bit more. I think I have the ability to, so I'm going to give it... Oh, maybe not. Let's see. I have to make sure you guys can see anything that I do here. So if I do that, you can still see it. 5, 10, 15, 20, 25, 30, 35. Okay, that'll work. So 5%, 10%, 15%, 20%, 25, 30, 35, and 40, and 45. We're shooting 5 We have 5 shots, so we're going to do 0, 1, 2, 3, 4, and 5. 0, 1, 2, 3, 4, and 5. Make a histogram out of that. Here's our K and our P of K. So I still have the values on my other side here. And I'm going to make bars for this thing. 0 is basically 0%. This, you basically cannot see it, but I will just draw something very minimal that pretend like you can. This other one's still also very small, 0.3%. It also should not very much show up right there, but there it is. These ones, tiny, 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 tiny. 2 free throws. You can at least visibly see it this time. It'll be 3.5%. So this will be probably around there. I hate the snap. 3 free throws. Now it starts to really build, and you get toward your 17%. So there's 15. Now it's actually, it's something of note. 4 is the highest one. This is where we hit 40.4%. Basically probably there-ish. And then 5 is 38.4%. A little under 40, not much. So 38.4%, like that. So that's probably a good idea of that histogram based on what we had up here before. And that's utilized down there. Now they say, what is the most likely outcome? 4 free throws made is the most likely outcome. Most likely outcome. 4 free throws made. Which makes sense with respect to the overall distribution. All right, guys, that's the last question, and that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching this Chapter 5 review. Hopefully you got a little more well-vested in the stuff. As fast as most of the problems may have been, I hope that it was just overall good coverage of saying, all right, there's this, this, and that, and the other thing. So, guys, thank you. Take care. I'll see you in the next one.